and welcome to our official start of Big Data for today. We have, I guess, two big picture ideas, things to talk about today. The first one is the last of the indexes that we'll be covering. It's called a RUM index, building off of that GIN index. We talked a little bit about it, but we'll do like 5 minutes or so of more detail about that. And then we'll get into more details for multilingual specific full text search. So I'll go ahead and share my screen. And what I have pulled up here is just the picture of the RUM index from that haber.com webpage that was references that we've been looking at for the other indexes. And this picture should look hopefully very similar to the GIN index that we were talking about before. So it's kind of good to have it split up over multiple weeks talking about this index, just to give you another refresher on the GIN index as well. And you see up here our B tree with these white boxes are the different lexemes or words or tokens or elements in our vocabulary. All of those are synonyms for each other. And when we have our TS vector, that's the type that contains the information about the document, all the words in the document. The TS vector is represented in here. And then the TS query is what we actually do the query with. And with the query, we would follow for each of the words down using the B tree operations to get these black boxes that correspond to the particular tuples or TIDs that are the documents that contain those particular words. And then depending on whether our query had ands or ors in it, we would and those. So this is called the posting tree right here, this big tree of all of these different black TIDs. And then here's the posting list right here. The posting list, we use a list when it's small, and then at some point it converts into a tree when it's larger so that we can do faster ands and or sort of operations between these data structures. So all that's the same between the GIN and the RUM index. The RUM index does everything the GIN index does, but then it does a little bit more. The RUM index has these gray boxes as well. If you look back at the GIN index picture, it doesn't have those gray boxes. And these gray boxes are meta information associated with each of the tuples. And so that meta information can be anything that you'd like it to be, but in particular, some common ones are like the page rank of a particular document. The page rank is sort of what Google famously used for ranking web pages way back when they first started. They still use the page rank a little bit, but now they have a more complicated system that they don't fully disclose. Or besides the page rank, you could include information like the date that the article is published on, or any sort of other information like that that you might want to sort the order of the articles by. And because this information is included directly in the tree, you can then do the sorting of your results directly inside of the tree data structure without consulting the heap or the table. And you can do index scans that way, not just bitmap scans, or index only scans and not just bitmap scans. So the only difference between the RUM and the GIN index is that the RUM index stores this extra information as well. As far as like what does, say, Google or Bing actually use in their implementations of search, it is just this RUM index. They're not using Postgres. They have their own custom systems. So they don't call their index the RUM index. And there's going to be slight differences between Postgres's implementation and their implementation. But this is what it is. It's a generalized inverted index, which is what GIN stands for, that stores some extra meta information, which is their rankings. And then the secret sauce about what makes Google search results good or Bing search results good or Baidu results good is not the data structure itself, it's just what they're choosing to store in this meta information here. So it's a super quick review of what we talked about last time and this RUM index. Are there any questions about that? Okay, so then today we're going to stop talking about the search data structures in particular and start talking about the actual text part of the full text search. So these data structures, whether they're GIN indexes or RUM indexes, those are sort of a general data structure that you can use no matter what language you're doing full text search with or what specific techniques that you're trying to do. And the language-specific processing will happen before going into those data structures. And it's that language-specific processing that we're going to talk about right now. For what we'll see is that when we were working with this Twitter data set, even though it was multilingual, Twitter supports about 60 different languages and more than 100 languages are known to be used actively on Twitter. We didn't have to do any particular special language specific processing because Twitter was actually doing most of that for us in the back end. When we start working on actual web pages, which is what we're going to transition to now for the rest of our programming assignments, working on that web project that I promised you at the beginning of class we would be getting to. When we're working on that, there's nobody who is like in charge of the internet enforcing that everybody does good things with their text. And so we're going to have to do those good things ourselves and understand how to do that, how to work with text other than English in an effective way. And so we'll talk about that today, probably a little bit on Wednesday too. And then once we've finished that, we can talk about the actual, the web search applications. I mentioned last time that you have your Twitter Postgres 2 assignment is due this coming Sunday. And so that's an actual coding assignment. You'll have to write a bunch of Postgres SQL code for that. There is also a homework assignment for this week. It is another one of the PDFs that is really just intended to prepare you for the final exam and what sort of questions will be on the final exam. Yeah, this particular PDF file, there's nothing required for you to turn in. It's just really meant as a review. And so once you have reviewed it to your satisfaction, you just enter this sentence into Sakai and you'll get full credit on the assignment. The assignment's not worth a whole lot of points. I think it's just worth 3 points. But that's how you get the credit on the assignment. Are there any questions about just the mechanics of what to do for the homework assignment? Okay, then we'll get started on Unicode. So if we were in person, one thing that I would do is do a quick survey of everybody right now about how many people have experience with Unicode before. And since most of the class is asynchronous right now, I'm not gonna do that. But one of the things that I found in the past is that basically no computer science departments or computer science education programs, at least in the US, teach Unicode as part of their curriculum. And this has been my experience at now 5 different universities, colleges around the country. And I think that's a huge shame because in my opinion, Unicode is definitely the #1 most important concept for any practicing data scientist or computer programmer. And the reason for that is that Unicode is not just a system for representing every possible language using computers, but it is the system that everybody in the world uses. And if you don't understand this system, then you cannot work with text that is not English. And even if you are only using English text, you'll still run into situations where you're going to get weird bugs and you don't understand why, if you don't understand the foundations of Unicode. So I know a small number of you have taken classes with me before and seen some of the stuff that we're going to talk about today in Unicode, but there'll be some new stuff related to Postgres specific issues here for you all. And for everybody else, then if there's one thing, like only one thing that you're going to use in this course and the rest of your careers, whatever those careers are, I think it's going to be this, this week's worth of lectures talking about Unicode and multi-language support. Okay, so yeah, Unicode is this system for every possible language using computers. It's developed by thousands, literally thousands of PhD level linguists and computer scientists. So it is an incredibly complicated system because human language is incredibly complicated. And it's not something where really there's no individual person who understands all of Unicode. Instead, so we're definitely not going to cover all of Unicode in this class. Instead, we're going to cover some of the general principles about how Unicode works and how to work with multilingual text, so that when you encounter these sorts of weird situations, you're able to both debug them when they do occur and avoid a lot of the pitfalls that that cause them to occur in the first place. And so avoid these bugs, prevent them from actually happening. And again, as a practitioner, actual programmer or data scientist out in the real world, most people, even people who are not working natively with English language text, but working in other languages, don't really fully understand Unicode. And so having this background can sort of set you apart as like the wizard on your team, able to do things that other people can't. So Unicode, the system, was developed in the 1990s is when people first started working on it. It's been about 30 years now since the first Unicode 1.0 specification. I think we're on version 12 or 13 now. Just coincidence that it's similar numbers as Postgres. And it replaced country and language specific systems before. So ASCII is something that's still widely taught in the US about how computers represent text. And it's because it was pioneered in the US for English language text. This system right here, KOI-8, is the Russian system that was pioneered in the Soviet Union. And both of these two systems were sort of competing with each other for a while until Unicode came along and superseded both of them. This is a fun comic that after we've talked about all of the Unicode stuff today, will hopefully make more sense about the details of what this comic is actually saying. And you can find a link here about the explanation, but we won't talk about it in detail. So we'll do most of the examples today in Python because it's a little bit, it's just syntax wise, it'll be a little bit easier to understand what's going on. And one of the reasons why Python initially gained so much popularity was because it was really the first language to have good native Unicode support. So any programming language, especially nowadays, you can do this Unicode programming, multilingual programming in. But if you're in, say, C, C++ programming languages, it's really awkward to do it, really difficult to do it. Python, it's 99% of the time, you don't even have to worry about it. Really smooth. One of the differences, though, between Python 2 and Python 3 is really the main difference about why the two versions had to split is the way they handle these Unicode conventions. Python 3 chose the system that's best for pure Python developers. So everybody who's in the data science major at CMC, this would be sort of the camp that you fall into. Python 3 is really tailored for you all. And for CS majors, sometimes you'll fall into this camp, but sometimes you'll be working with other languages too. And Python 2 really has the most convenient system for that. So even today, so this split happened, I don't know, like 8 or 9 years ago at this point. Even today, probably about 10% of Python users are sticking with Python 2. And the main reason for that is because of the way it handles Unicode. They prefer that. Okay, so now let's talk about the details of actually like what is Unicode and how it works, some of its theory. The first key vocabulary to understand is the word code point. And a code point is a combination of a number and some particular character. So every one of these letters that we see right now has a particular code point associated with it. And for other encodings that you may have seen before, like the ASCII encoding, that code point was actually the number that was stored on your hard drive physically when you save a file to disk or write a string into memory. But in Unicode, a code point is not the number that's actually stored on your hard drive or in memory. Instead, we have multiple different systems for representing these code points in memory. And those different systems are called encodings. So an encoding is a way of mapping the code point number into a particular byte sequence. There's two popular encodings, UTF-8 and UTF-16. Let's say UTF-8 is the most popular. UTF-16 used to be the most popular, but it's being phased out now. And we'll talk about why that is in a second. Let's see, I think before going into more of these theoretical details, I think it makes sense now to switch over to Python and take a look at the some of the practical details that'll make this discussion a little bit more concrete. So I'm going to switch right now screens to right here. I'm in my week 12 folder of the class repo. And up here, what I have opened in Vim is a file notes.py. There's notes.py, and it's in the repo, and you can take a look at it. And originally, this was something that we were going to talk about on Cesar Chavez Day, in honor of Cesar Chavez, that he's a non-English words right here. He was Mexican, and how to actually represent his name in both Python and Postgres. But I pushed that off to today because of having my baby then. So we'll have our delayed celebration of Cesar Chavez Day today. And what I'm going to do is I'm going to open this notes.py file in Python down below. So Python 3-i notes.py. And we have these three strings up here that all look like they are the same, Cesar Chavez. But if I did something like string 1 equals string 2, we would get false. And string 2 equals string 3, false. And string 3 equals string 1, false. Despite the fact that all three of these strings look the same, they are, in fact, different strings. And the reason they are different strings is they are represented by a different series of Unicode code points. These strings look the same, but they are a different series of Unicode code points. And one of the ways that you can check that is with the length function in Python. We do length of string 1, string 2, string 3. You see that all three of these strings have 3 different lengths. With the length function in Python, and actually every programming language that does Unicode natively, so it's the same in Postgres as well, what this length function does is it actually counts the number of code points in the string. It doesn't count how many visible characters you see. So lang returns the number of code points in the string. And what's happening here is that each of these strings is being represented in different forms using a different series of code points. So text in Unicode does not have a single representation, but can be represented in different ways. And each one of these 3 strings is using a different way to represent this string here, Cesar Chavez, and because of that, none of them are equal to each other. If we were, so let's zoom out for a second and think about why is this important from a high level, big picture idea. Well, there's going to be many web pages on the internet that talk about Cesar Chavez, and each web page can choose to use whatever form of that it wants to represent his name. And so when they're doing that, if they use form 1, but we search for form 2, like this, we search for this Cesar Chavez, but they used this Cesar Chavez here, we're not going to find that web page in our search results. And so what we have to do whenever we're working with text that comes from a user input, what we call an unsanitary source, we have to sanitize that text and normalize it into one common form. So anytime we get text from the user, whether that is like they type it in on the keyboard or they load it from a file, download it from the internet, anytime it's from somebody who is not us, we have to convert it into a common, what's called normal form. And in Unicode, there are 4 different normal forms called NFC, NFD, NFKC, and NFKD, 4 different normal forms. We're going to talk about, in particular, NFC and NFD, but for the homework and the final, you're also responsible for knowing about these 2 normal forms here. And so my expectation is that you'll be able to look those up with the links that I have provided in the notes to get the details about these normal forms. Okay, so let's start taking a look about what these about what it means to be in a normal form and the strings, what normal form they're in. So what I'm going to do first of all is convert each one of these strings into an ASCII representation. So in Python, there is a function just ASCII. You do this, like this, and then every character that is not an ASCII symbol, so basically not a normal English letter, plus punctuation and spaces, will get converted into some sort of escaped representation like this. So here, \XE1 is a sequence of letters that you can type into Python, and it will give you the exact same string as this string right here. So in order to see that, I'm going to copy and paste that string right here and say equals, and then C\XE9 SAR space CH \XE1 VEZ, like that. And that time we get true. So here, in this string, they don't look like each other, but they are actually equal to each other, because here, this character right here is actually equal to this character right here. \XE9 equals E with an accent mark on top of it. But now let's take a look at string 2, the ASCII representation, like this. And when we look at the ASCII representation of string 2, we can see that this representation here is different than the representation that we had up here. Here we have the letter E actually represented as an E, but then there's this big sequence right here, \U0301, which is just the accent mark by itself. This is what we call a combining character in Unicode terminology. And what a combining character does is it takes the previous character in your sequence and modifies it. In this case, adding an accent mark over it. Because this sequence of code points right here, when you do ASCII, you get the sequence of code points out. This sequence of code points is different than this sequence of code points here. That's why these 2 strings are not equal to each other, even though this E accent mark and XE9 represent the same character semantically. So what we want to be able to do is be able to convert these 2 forms back and forth into each other, and that's called normalizing these strings. Currently, this one is in what's called NFC form. NFC stands for normal form composed. NFC equals normal form composed, and NFD equals normal form decomposed. So this is called composed because we have composed the E accent mark into a single character, and this is called decomposed because we've separated out into 2 separate characters. In Python, in order to convert one string into another, in order to normalize one form into another, there is a built-in library called Unicode data, and Unicode data.normalize is the function that you would use in order to do this normalization. The way this will come up in your next homework assignments is that you're going to be getting text from the internet using Python, basically crawling web pages. And then before taking that text and sticking it into Postgres, you'll have to normalize the text into some particular form. It doesn't matter which form you pick, whether you pick NFC, NFD, NFKD, NFKC, doesn't matter, but you have to normalize it before sticking it into the database. Otherwise, the database operations, when you do equality comparisons, it will say that these two things are different, and so Cesar Chavez is not Cesar Chavez. In order for it to say that they're the same, you must normalize before sticking it into the database. And you'll do that with this function here in Python. So here, in order to normalize, I said before that string 2 is in NFD form, denormalized form, because it has these two strings separated out. So I'm going to normalize it into NFC form, like this. And it returns the result in NFC form. The result looks exactly the same as just the string itself. But you see that if I compare them, equals string 2, now we get false, because this string 2 right here, the string 2 right here, both of those are in NFD form right now. And then this function here converts it to NFC form, converts it so that the ASCII representation, the set of code points being used, combines the E and the accent into one single code point like this. So because this is now in NFC form, if I were to take this and compare this to str1, we'll get that that's equal to true, because str1 was already in NFC form. Anytime, so again, the main takeaway here is that anytime you have a string from that you've gotten from somewhere else, normalize it into some form, and doesn't matter what form you pick, but as long as everything's in the same form, equality and text search will work as you expect it to. Are there any questions so far?
Even if we normalize, how does that ensure that we'll be able to match the string on a web page, which might be using a different form or something?
So what we'll end up doing is that what we want guaranteed is that every string that's stored in the database, so the strings that you're actually doing the search on with your GIN index and the TS vectors, we want those strings to be guaranteed to be in some particular form. So even if the web page, say, is in NFD form, when you convert it into NFC form to store it in the database, you'll be storing a technically different document, but semantically it'll be the same document. And because it will be in NFC form in the database, when you do the search in the database, it will stay, the equalities will work. I'm not sure if that answered the question or not.
Yeah, that makes sense.
Okay. Yeah, a lot of these, I think from my personal experience, a lot of these like Unicode functions and sort of why we care about them and what exactly they do, they won't really fully click necessarily until you actually start writing the code that we'll get into in the next assignment. So yeah, try to get as much of the sort of foundational theory knowledge as you can from this, but then it's the next assignment that'll hopefully make it a little bit more concrete. Good question. Any other questions so far? Okay. So in Python, when a string is being stored in memory, Python always stores code points in a string object. And if you want to actually say save this string to a file, then you have to first convert those code points into a sequence of bytes. And that again is called encoding the string. And in Python, the way to do that is every string has a method called encode, and you can pass the name of your encoding into this function. So the most popular one again is called UTF-8, and this here is the encoding for a UTF-8 string. You'll notice that at the beginning of the string, it starts with a B character over here. This B stands for bytes. So this is technically in Python terminology called a byte string, and it's no longer a string. And now Python guarantees that in a byte string, every single character can take up at most 1 byte in memory or on the hard drive, wherever you're storing it. And if we compare this to the ASCII representation of string 1, you'll see that here we had the XE9 code point right here, but that code point, one code point, got converted into 2 separate bytes right here. And that's just a property of the UTF-8 encoding scheme, is that some code points will be encoded into multiple bytes, some code points will be encoded into a single byte. Each one of these characters right here, just to sort of maintain readability, they represent a single byte, and rather than writing them out in the \x form, they just write out the character like this. This, I don't think I mentioned this yet, this \x form, the format of this is that if you have \x and then 2 numbers, I'll call them capital X and capital Y, X and Y must be hex numbers. So any numbers between 0 to 15, where numbers 10 plus are stored as A, B, C, D, E, and F. So A is 10 up to F being 15. And if you have 2 hex numbers next to each other, well, each hex number can be stored in 4 bits. So 2 hex numbers is 8 bits or 1 byte. So each \x corresponds to a single byte in your byte string here. If we take the length of the encoding like this, we get the actual number of bytes that are required to encode your string. And one of the properties of the composed versus the decomposed normal forms is that because the composed form is guaranteed to have fewer or no more than the number of characters as the decomposed form, the composed form is also going to have fewer bytes in its representation. For that reason, when people store text in databases, it is NFC form is the most common to use because it uses the fewest amount of bytes. Let's see. There's a little bit more to talk about encodings, but before we do that, we need to talk a little bit about non-English and non-Latin based languages. So I'm going to move us down here to see some more interesting examples of languages in Python. So here's just some English variables, English 2. The only difference between these is that over here, there's some sort of funky punctuation marks over here. These exclamation points are actually different than these exclamation points. These are from the Chinese section of the Unicode code point range. It's totally okay to mix languages as much as you want. Here I just have mixing the punctuation, but down here I could do something like English plus Chinese plus Arabic plus English again, and we get this nice little combined text, and that's totally okay. You're not required to, or you're not limited to just one language per string. Let's see, all of these characters can be represented in both composed forms and decomposed forms, and they can also be encoded using both UTF-8 and UTF-16, among a number of other different encodings. And one of the properties of UTF-8 is that it's really good for English text, but it's fairly bad for Asian text. So if we take, for example, I'm going to take the English.encode into UTF-8 like this. So this converts that just into a byte string instead of a normal string. And let's take the length of that to see how many bytes that uses up. It uses up 35 bytes. If we compare that to an alternative encoding like UTF-16, UTF-16 we can see uses up 72 bytes for the same English text, the same English variable right here. And so for English text, UTF-8 is basically always used because it's much more space efficient. But that's not true for foreign language text, especially Asian languages. And so let's take a look at this Chinese language text right here. And so I'll do Chinese.encode. We'll start with UTF-8. Takes 36 bytes to store this string right here. So basically the same amount as that it took us to store our English language variable. All of these different strings in the other languages, they're just Google Translates of this same English text right here. So it makes sense that something that's the same semantically, same sentence is going to take up roughly the same number of bytes. Now let's convert that into UTF-16, and you can see that for the Chinese text going from UTF-8 to UTF-16 reduced the number of bytes needed to store the text. But for the English text going from UTF-8 to UTF-16 increased the number of bytes needed to store the text. And so let's talk a little bit about why that's the case. And to do that, I'm going to switch over to the notes that talk about UTF-8 and UTF-16. So the reason for that is for UTF-8, Latin characters are guaranteed to take 1 byte per code point. If you have Arabic, Cyrillic, Greek, Hebrew, basically any other sort of Westernish language, they take 2 bytes per code point. And then really any Asian language takes 3 bytes per code point. A few rare Asian characters and then emoji also take 4 bytes per code point. So UTF-8, most efficient for this, least efficient for this. UTF-16, here the difference between, I guess, what this 8 stands for is the number of bits used to store a typical character, where here the typical is assumed to be like English language text. UTF-16, here 16 is the number of bits taken to store the typical character, but now a typical character is basically a character from any widely used language. So now most European and Asian languages use 2 bytes per code point for the vast majority of their characters. For English, that's sort of inefficient. That's why we used double the number of bytes. But for Chinese, that's 2 bytes per code point is a lot better than 3 bytes per code point. And so Chinese, Chinese is more efficiently stored in UTF-16. This is the typical sort of trade-off that you get when switching between UTF-8 and 16, depending on which language that you're in. You get use about 1/3 less space for Asian languages, but 50% more space, twice as much space for English or other Latin-based languages. In terms of like, let's see, so these days, the vast majority of people use UTF-8 for everything. Certainly everybody, let's say 99% of people in the US and Europe use UTF-8 for everything. If you're in Asia though, or if you're say scraping an Asian web page, a lot of these Asian sources stick to UTF-16 specifically because it's much more efficient for them from both a bandwidth perspective of how much data they have to transfer to people and a storage perspective of how much they have to store themselves. The sort of default for Postgres, any Postgres database, is to be in UTF-8, but you could change it to UTF-16 if you wanted to for if you were really only storing Asian language text and wanted to maximize your disk space or your disk usage. That's not very commonly done, though, to adjust the database internal settings. Instead, it's you just have to know that some of the web pages that you'll be scraping will be in this UTF-16, and we'll have to be able to accommodate that. One last point about UTF-16. So there was a big push, say around 2000, for by both Microsoft and Java from Sun Microsystems to make UTF-16 the sort of default Unicode representation, but that basically fizzled out because English speakers were upset about that, and they were upset that they had to waste their bandwidth, and so they invented UTF-8 as an alternative, and you can see that UTF-8 very quickly rose in popularity and is sort of the main one that people use now. You've probably seen like garbled text in different places where, especially if foreign language web pages, and the reason for that is because your web browser has interpreted been using the wrong encoding to interpret the web page, and so instead of saying "I heart Unicode," you get something weird like this question mark. Any questions about encoding issues in Unicode?
I was curious about what is the difference between like the NFCs and all that stuff? Was that like a decoding method?
That's a
How is
good
it
question.
different from?
So normalization and encoding are two separate concepts. And you can have any normalization scheme with any encoding and any encoding with any normalization scheme. And this is really easy to get confused. So if we, in the Python only world, the way to think about this is that normalization only affects string types. Where to put this? We'll put it right here. So normalization is a function from strings to strings, and encoding is a function from strings into bytes. And so here, when I did Unicode.normalize of NFC, string 2, Unicode data.normalize, without the D, there.
You've spelled normalize.
Yes, thank you. There we go. Here, this, when I called Unicode data.normalize, I got a string as output. And I know I got a string as output because there's no B in front of this string. So this is just a sequence of code points, these abstract numbers that we don't know how they're being represented physically with bytes. And different versions of Python actually implement these strings differently with different default encodings. But whenever you do this .encode function, this is going to change it to this actual sequence of bytes B over here. And one thing to notice as a difference is when we encoded into UTF-8, this E\9 right here. So this is where the E accent mark is. The E accent mark actually takes up 2 bytes in the UTF-8 encoding, even though it's only a single character. When it's represented as a string down here, it's represented as just a single code point. And I know it's a single code point because this \xe9 represents a single code point. But up here, it represents 2 different bytes. 2 different bytes are needed to store that single code point. If I were to change this to UTF-16 and take a look at the results, here we get a bunch of different bytes spread out, and we can't even, all of these bytes are in weird ranges where it's difficult to even visualize what they are. So yeah, the NFC, NFD normalization converts from one set of code points to another set of code points. The encoding actually converts it into how you physically store it on the disk. So this is a purely semantic transformation, and this is a storage level transformation. When we're doing the web scraping, the thing that you really have to care about the most is this NFC NFD normalization. This is something that has to happen at the application level and can't happen, say, at any level prior than that, because the application is the one who's going to be doing the equality comparisons and needs to know which normal form it's in. The encoding is something that will happen at the database level and it will be completely transparent to us. So all of the Docker images that we'll have, the encoding will be UTF-8, and so things will just work. We'll be using a little bit more disk space than necessary for the Asian web pages that we download, but that's okay. Did that answer your question, Satvik?
Yeah, and also so you said that we can convert from strings to bytes using encoding. So how do we convert back from bytes?
Good question. So anytime you have a byte object, so I'll copy and paste this down here as a byte object, those have a method decode. And with this decode, you pass in whatever encoding system you use to do the encoding, and you get back to an actual string object. Notice the lack of a B here, meaning it's a string object. If we were to say, try to decode with a different system, sometimes you'll get an error like this. Sometimes you'll get a, so here, let me first encode UTF-8 and then decode UTF-16. It'll just, so string 2 was supposed to say Cesar Chavez, but we converted it to UTF-8 and then deconverted it using UTF-16. And because these two things here didn't match, we get these random Asian characters. There are some tools that can help you sort of identify which encoding a byte string is in. In this case, I know enough of Asian languages to know that these are Chinese symbols, these are Korean symbols here and here. It doesn't make sense to have Chinese and Korean symbols sort of intermixed with each other. And so this can't be a valid decoding of that byte string. Or it technically could, it's just extremely unlikely. Nobody would actually want this semantics of whatever this means. And so there are tools that use machine learning under the hood to try to guess what an encoding is for a byte string. But really, if you're given a byte string, you also need to somehow be given and told what is the encoding of that byte string in order to work with it. A lot of web pages on the internet are misconfigured where they will tell you they are one encoding and they're actually in another encoding. And this makes scraping those web pages really, really difficult. The typical sort of practice is to make a best effort guess, and if you're wrong, then you can't search those web pages or you can't analyze those web pages. Good questions. Any other questions so far? Okay, so a couple things to note about foreign languages is that languages are, so we probably all understand, have an intuitive sense that languages are complicated. But however complicated you think languages are, I guarantee they are much, much more complicated than you think they are. And so here are some examples of different languages and some of the complexities related to them that you might not have thought about before. So Here, this Chinese string, you'll notice that there are no spaces in this Chinese string here. And so that makes tokenization of this string really difficult. How do we extract the words from this string so that we can do full text search over words? For English and most languages, that's not too hard to do. You just find the words based on where they have spaces between them. Can't do that in Chinese. Vietnamese is sort of the opposite. Vietnamese puts spaces even in the middle of words. They just separate every syllable by space. And so, again, you can't use spaces. You need some sort of more sophisticated system to know if this right here is one word or two separate words. Korean is traditionally written without spaces, but typical modern web pages will put spaces in there, since Korean's been highly influenced by English and Latin languages now at this point. Arabic is traditionally written, basically always written from right to left. If you know any Arabic, then this will look really, really weird to you because this here is being displayed in left to right. I have my terminal set to always display things in left to right, even for languages that are right to left, just because that makes it easier to work with from a mechanical perspective. That's going to potentially confuse our scraping algorithms and the algorithms that we write to deal with Arabic, that we'll have to keep in mind that the order that the bytes are processed in is different than the order that an English speaker would expect them when they're being displayed. This really has a big impact when you're if you're trying to display the results of a web page of search. How do you display the results that contain both Arabic and English together in a way that's like meaningful to people who speak those languages and not nonsense? Emoji characters, again, can be represented in Unicode. Here, currently, my terminal has the happy face emoji font installed. This one right here is the poop emoji, and I don't have that one installed on my terminal. So we get this weird display character like this. German is actually a fun language because of this letter right here. So certain dialects of German allow this letter, certain dialects do not. And I want to see what happens when we convert this word right here. So German, when we convert it to uppercase, we do upper of German, upper, German dot upper like that. You can see that the German variable itself had this letter here, but it got expanded into two separate letters when we did uppercase. So the length of this string, the uppercase version, is different than the length of the lowercase version. And if we take that uppercase version and then convert it back into lowercase, you see that these two capital S's get converted down into a lowercase s, and they do not get converted back down into this letter right here. So for English, going to upper and lowercase is, if you start in lowercase, go upper and back to lower, then you're back to the same string. But that's not true in every language. Another problem is that numbers are represented differently in different languages. So here, if we look at this string numbers and we try to convert it into an integer, and you were just naively looking at this string, it looks like it has an 8 and a 9 in it, but that's actually the number 47 in the language Tamil. And so it's very common for, maybe not very common, but occasionally people who are trying to break computer systems will write out their numbers using systems like this, and people will look at it and say, oh, it should be 89, but it's actually 47, and so weird behaviors will result. Here we have in URL1 and URL2 right here, URL1, URL2. Again, they look like they should be equal to each other, but they're not. This is false. So we talked about normalization before, and so maybe our instinct should be, let's convert them both to the same normal form. Let's do Unicode data.normalize NFC of URL1 and compare that to Unicode data.normalize NFC of URL2, like that. And we still get false. The reason these two strings are not equal to each other is actually because this B and this O and this A right here are Greek letters and not English letters. And it just so happens that in the font that I have installed, Greek letters and English letters use the same picture. If I were to convert them both into ASCII so that we could see the code points, you see that for URL1, it gets just represented in English. URL2, we get these weird characters right here representing the Greek uppercase letters for those letters. If we were to convert URL2 into lowercase like this, there we can see the actual Greek letters. But even for the O, the Omicron, both the lowercase and the uppercase use the same font picture. So this can be really tricky when you're trying to have these edge cases scraping things from web pages. And there are plenty of web pages that have formats like this that are basically designed to trick people into giving their Bank of America passwords to false web pages. There are lots of sort of security implications of Unicode like this, and the NSA, National Security Agency, actually has a nice publication about that right here. If you're interested in trying to hack people using Unicode, this is a good resource for that. I'll say that, so when I was in the Navy, I worked at the National Security Agency doing these sorts of things, and this is a actually widely used thing that both people use against the United States and that the United States uses against other people. Let's see. So yeah, the main takeaways from this discussion is that if you have a string, you absolutely must know, you can't just trust the string as it is, you must know both the encoding and the normalization of that string. Sometimes you can sort of get the encoding from just the raw bytes, but not realistically, you can't do that. You shouldn't trust in that. The normalization form, you actually could compute the normalization form, but it's a linear time operation, O of n, relatively expensive to do if you're doing that over the entire internet. So also something that you just don't do. Instead, what you do is you trust Postgres will handle the encoding issues for you, and whatever your web scraper is that you're using, you'll have to make sure it's designed to handle the encoding issues for you. But then the normalization is something that you have to do yourself. Fix something, again, NFC is typically the default, and use that everywhere. This is a really famous article about Unicode. Definitely recommend reading this article. And then here's the reference that we'll be using about Postgres specific notation. And there's not really too much here to, this is sort of the only main things that you can check if a string is normalized in a certain form using these commands right here, just the string, the text is, then the form normalized, or you can use the normalize function to actually do the normalization for you. And these are SQL standard things, so any database that supports the standard will work with this these same forms. Despite the fact that Unicode is now about 30 years old, and UTF-8 is now about 20 years old, proper database support for these foreign language encodings is really, really recent, and especially in non-Postgres databases. So MySQL had this really famous bug where their UTF-8 implementation could support a maximum of 3 bytes, but some UTF-8 characters like emojis take 4 bytes and certain Asian characters. And so they've just recently fixed this, but you have to not use UTF-8, what they call UTF-8. You have to go through a whole bunch of hoops to get things to work. So this, again, is sort of one of the high-level differences between philosophical differences between Postgres and MySQL is that Postgres, we 100% care about both standards and the correctness of our data, that if we insert something, it's guaranteed to be in there. MySQL, they mostly care about those things, but they will sacrifice those things for ease of implementation or for speed. Okay, so now that we've talked about the big picture Unicode ideas, we're going to talk about the actually doing full text search in Postgres on these multi-language strings. Are there any other questions on Unicode in general, though, before we dive into Postgres in particular? Okay. So the first thing is this pspacey library. I've got a link right here. And if you click that link, then you'll notice that this library doesn't have actually really a README file at all yet. Typically when I'm, so this is a library that I've been developing, and typically when I'm working on a project, I like to do it all out in the open, not have a private repo, keep everything public. I just don't put my README files or things in the main master branch until I'm ready for other people to look at it and sort of ready to publish it. So here I have this notes branch of the repository, and that's where you'll find the README that has the explanation here about both this library in particular and sort of Postgres multilingual support more broadly. And so the goal of this library is, so it's a Postgres extension. It's something that we can add onto Postgres. Postgres has really good support for adding on libraries. And the purpose is highly multilingual for full text search. And so 3 main goals: using a large number of languages, being correct, including the ACID compliance, and being really fast. So it currently has 58 languages supported, in particular Chinese, Japanese, and Korean, all the main Asian languages as well, Vietnamese, Thai, Indonesian, and a lot more. And none of these languages are sort of natively supported by Postgres. So if you wanted to do full text search in Postgres in any of these languages, you'd have to use either this extension or some other technique. If you compare this to those other systems that we were talking about before, they all have a much smaller number of languages that they support. And then this Groomga system, technically it can support any language, but it's really only good in Chinese, Japanese, Korean, and English. If it was outside of that, I wouldn't trust it for anything. The key idea of this pspacey library, and the key, what I think is a fault of all of these other systems, is that these other systems, they try to do both the text processing and the search in a single component. So the developers of the library have to be experts in both text processing of all the languages that they're going to support and developing these data structures for fast search. The idea of pspacey is that the Postgres devs are really great at developing data structures for fast text search. And then there are natural language processing people who focus specifically on just processing natural language, independent of the downstream use cases. And those people these days hang out in this spacey library in the Python world. There's a good library that's highly multilingual, supports all of these languages that pspacey does, used for lots of different natural language processing applications. And this library essentially connects those 2 groups of people so that the data structures people get all the advantages of the work that the NLP people are doing, and the natural language processing people get the advantages of the work that the data structures people are doing. And that work is sort of automatically transferred between the 2 groups of people without them having to do anything. So we'll see how that works here down in a second. Maybe one of the Disadvantages of sort of Postgres libraries as opposed to, say, Python libraries is that Postgres libraries are relatively difficult to install. There's no just like pip install command that you can run to get the Postgres library. So in this repo, there's a Docker file, and you can use the Docker file to get access to it. Or there's a shell script that I've written that the Docker file uses that will install all the dependencies for you. But it's kind of a pain in the butt to do to actually get it installed. And that's just relatively true of any of these Postgres libraries. It's more broadly true for any of these lower level programming languages like C, C++, that these languages came about before the advent of what we call package management systems. Pip is an example of a package management system. And Python was being developed about the same time as these package management systems were becoming popular and widely used. And so that's why Python has this pip system, but because Postgres, it's written in C, does not have any sort of good package management system. Okay, so examples of using this library. So creating the library requires running Python from within Postgres. That requires creating what's called a language extension with this command, and then actually creating an extension enabling pspacey is done with this command right here. And I'll go ahead and switch my terminal over to here, where I have this pspacey project opened up, and connect with psql. There we go. And let's create language pl python 3u that. So PL stands for programming language, Python is the name of the language, 3 is the version number, and then U is, I'm not sure what U actually is, but it's at the end of all the Python and all the most of the programming language extensions. And then create extension pspacey like this, and it creates the extension. This extension comes with an alternative function that you can use instead of the toTSVector function to generate TS vectors. And so if we did something like select spacey underscore TS vector, we'll do English and say this is a test. This is the example that we did before. You can see that here is our result. This is the same result that we got when we did toTSVector with English like this. We get test of 4. The first thing you might notice is that the spacey TSVector version was significantly slower at the very beginning. That's because the spacey system uses what's called a lazy loading for its languages. And that means it doesn't preload whatever language the models that it uses to do its parsing for whatever language you have loaded right here. Instead, the very first time you use a particular language, that's when it's going to load up that model into memory. And so the first time you run this command for any given language, it's going to take a couple of seconds, but then after that, it'll go fairly fast. The next difference between these two functions is that, so this uses the actual ISO code of a language instead of a name of a language. That's a lot more easier for people to work with, especially in these multilingual systems, because if somebody say doesn't speak any English but is a Spanish speaker, it would be weird for them to have to refer to their language as Spanish when that's not what they refer to it as. And so instead, using the language code ES would be much more natural for a Spanish speaker to do. And here, it's okay to use the wrong language to parse something. You just might get weird results down out here. Switch back over here. So here's a list of all of the languages that are supported. You can see there's lots of really weird scripts that are supported. And what I want to look at is this section down here. So generating the TS vector. So this is what we were just looking at in the actual terminal. Here, though, it's using, so we have English up here, Spanish here. Both of these languages are natively supported by Postgres, but then here's some Korean and Chinese, both languages not supported natively by Postgres. And so you can't use these languages without some sort of extension like this. The results down here are sort of whatever's inside of this string doesn't matter, or from the perspective of indexes doesn't matter. It's still going to be able to use the same gin and rum index and search for these strings just like normal. If we so here is how you can create those indexes, basically two different ways. One, creating one index on the entire table for all of the languages, and one that creates a separate index for each language using partial indexes. From a disk space usage, both of these two techniques are going to take up the exact same amount of disk space, but they'll have slightly different runtime characteristics because it's different sets of trees that you have to search for each of these. This is generally, it's a little obnoxious to type all of this out, but this is what we'll do for the web search assignment, that this is the most efficient. Last thing down here, there's some performance benchmarks. And so here is the runtime of actually calling the TS vector function on each of these different languages right here. And so these runtimes are in microseconds. So most languages are fairly fast. You could do thousands of these per second on your web server. If people are connecting, typing in search queries, no problem. Some of these, however, so like Russian and Japanese are particularly slow. It takes a whole 2 milliseconds to parse a Japanese string using this system. And so you can only do, say, 500 per second queries of this parsing on your web server on a single CPU. Let's see. This is probably a good stopping point for us. What we'll talk about next time is there's a few other extensions to Postgres that work totally differently for doing full text search. PG trigram, PG bigram, and again, this pgrunga one, we talked a little bit about it. And we'll see sort of the advantages and disadvantages of these and how they compare to the TS vector approach with pspacey. We'll see that all these other systems like Elasticsearch, Solr, Lucene, their techniques can be divided up into being basically exactly the same as these Ngram methods, or being the same as the TS vector method, just with less language support. And yeah, we'll do that next time, and then start talking about our web search engine. So that's it for today. I'll stick around and answer any questions that people have about homework or anything else or lecture today. Otherwise, I will see you all on Wednesday.